Quantum electrodynamics, QED. Quantum electrodynamics is the oldest, the simplest and the most successful of the dynamical theories. The others are self-consciously modeled on it. So I'll begin with a description of QED. All electromagnetic phenomena are ultimately reducible to the following elementary process. This diagram reads: charged particle E enters, emits or absorbs a photon gamma and exits. In this book, time always flows upward, the traditional convention. Particle physicists tend increasingly to let T run horizontally to the right, but there is no established consensus on the matter. For the sake of argument, I'll assume the charged particle is an electron. It could just as well be a quark or any lepton except a neutrino. The latter is neutral, of course, and does not experience an electromagnetic force. To describe more complicated processes, we simply patch together two or more replicas of this primitive vortex. Consider, for example, the following. Here, two electrons enter, a photon passes between them. I need not say which one emits the photon and which one absorbs it. The diagram represents both orderings, and the two then exit. This diagram then describes the interaction between two electrons. In the classical theory, we would call it the Coulomb repulsion of like charges if the two are at rest. In QED, this process is called molar scattering. We say that the interaction is mediated by the exchange of a photon, for reasons that should now be apparent. Now you are allowed to twist these Feynman diagrams around into any topological configuration you like. For example, we could stand the previous picture on its side. The rule of the game is that a particle line running backward in time, as indicated by the arrow, is to be interpreted as the corresponding antiparticle going forward. The photon is its own antiparticle. That's why I didn't need an arrow on the photon line. So in this process, an electron and a positron annihilate to form a photon, which in turn produces a new electron-positron pair. An electron and a positron went in, an electron and a positron came out. Not the same ones. But then, since all electrons are identical, it hardly matters. This represents the interaction of two opposite charges, their Coulomb attraction. In QED, this process is called Bhabha scattering. There is a quite different diagram which also contributes. Both diagrams must be included in the analysis of Bhabha scattering. Using just two vertices, we can also construct the following diagrams describing respectively pair annihilation, electron plus positron goes to photon plus photon, pair production, photon plus photon goes to electron plus positron, and Compton scattering, electron plus photon goes to electron plus photon. Notice that Bhabha and molar scattering are related by crossing symmetry. See section 1.4. As are the three processes shown here. In terms of Feynman diagrams, crossing symmetry corresponds to twisting or rotating the figure. If we allow more vertices, the possibilities rapidly proliferate. For example, with 4 vertices, we obtain among others, the following diagrams. In each of these figures, 2 electrons went in and 2 electrons came out. They too describe the repulsion of like charges, molar scattering. The innards of the diagram are irrelevant as far as the observed process is concerned. Internal lines, those which begin and end within the diagram, represent particles that are not observed. Indeed, that cannot be observed without entirely changing the process. We call them virtual particles. Only the external lines, those which enter or leave the diagram, represent real observable particles. The external lines then tell you what physical process is occurring. The internal lines describe the mechanism involved. Please understand, these Feynman diagrams are purely symbolic. They do not represent particle trajectories, as you might see them in, say, a bubble chamber photograph. The vertical dimension is time and horizontal spacings do not correspond to physical separations. For instance, in Bhabha scattering, the electron and positron are attracted, not repelled, as the diverging lines might seem to suggest. All the diagram says is, once there was an electron and a positron, they exchanged a photon, then there was an electron and a positron again. Each Feynman diagram actually stands for a particular number, which can be calculated using the so-called Feynman rules. You'll learn how to do this in chapter 6. Suppose you want to analyze a certain physical process, say molar scattering. First you draw all the diagrams that have the appropriate external lines, the one with 2 vertices, all the ones with 4 vertices, and so on. Then you evaluate the contribution of each diagram using the Feynman rules and add it all up. The sum total of all Feynman diagrams with the given external lines represents the actual physical process. Of course, there is a problem here. There are infinitely many Feynman diagrams for any particular reaction. Fortunately, each vertex within a diagram introduces a factor of alpha equal E square divided by h cut c equal 1 by 137, the fine structure constant. Because this is such a small number, diagrams with more and more vertices contribute less and less to the final result. And depending on the accuracy you need, may be ignored. In fact, in QED, it is rare to see a calculation that includes diagrams with more than 4 vertices. The answers are only approximate, to be sure, but when the approximation is valid to 6 significant digits, only the most fastidious are likely to complain. The Feynman rules enforce conservation of energy and momentum at each vertex, and hence for the diagram as a whole. It follows that the primitive QED vertex by itself does not represent a possible physical process. We can draw the diagram, but calculation would assign to it the number 0. The reason is purely kinematical. Electron goes to electron plus photon would violate conservation of energy. In the center of mass frame, the electron is initially at rest, so its energy is mc square. It cannot decay into a photon plus a recoiling electron because the latter alone would require an energy greater than mc square. Nor, for instance, is electron plus positron goes to photon kinematically possible. although it is easy enough to draw the diagram. In the center of mass system, the electron and positron enter symmetrically with equal and opposite velocities. So the total momentum before the collision is obviously zero. But the final momentum cannot be zero since photons always travel at the speed of light. An electron-positron pair can annihilate to make two photons but not one. Within a larger diagram, however, these figures are perfectly acceptable because although energy and momentum must be conserved at each vertex, a virtual particle does not carry the same mass as the corresponding free particle. In fact, a virtual particle can have any mass, whatever the conservation laws require. In special relativity, the energy E, momentum P and mass m of a free particle are related by the equation E square minus P square C square equal m square C to the power 4. But for a virtual particle, E square minus P square C square can take on any value. Many authors interpret this to mean that virtual processes violate conservation of energy. See problem 1.2. Personally, I consider this misleading. At best, energy is always conserved. In the business, we say that virtual particles do not lie on their mass shell. External lines, by contrast, represent real particles, and these do carry the correct mass. Actually, the physical distinction between real and virtual particles is not quite as sharp as I have implied. If a photon is emitted on Alpha Centauri and absorbed in your eye, it is technically a virtual photon, I suppose. However, in general, the farther a virtual particle is from its mass shell, the shorter it lives. So, a photon from a distant star would have to be extremely close to its correct mass. It would have to be very close to real. As a calculational matter, you would get essentially the same answer if you treated the process as two separate events. Emission of a real photon by star followed by absorption of a real photon by eye. You might say that a real particle is a virtual particle which lasts long enough that we don't care to inquire how it was produced or how it is eventually absorbed.